Section 22.2, Motional EMF. So let's take a look at the EMF that's induced in a moving conductor. So if we have a conductor, a chunk of metal, and it's moving through a magnetic field, then all of the charges in this chunk of metal are moving to the right with a velocity v. We can then use our right-hand rule to note the forces that will act on these charges that are, since they're in a conductor, they're free to move. So to do this, we'll put our thumb in the direction of the V, right? And then our index finger needs to point into the screen because the X's show going into the screen. And then our next finger, the middle finger, or our palm, would then point upward as the force. And we could show our other two fingers that we don't really use here on the side. So that's an attempt of the hand, right? For me, it looks like this. I encourage you to try it too. I have my velocity going to the right, my magnetic field going into the screen. So you need to point yours back at me. And then that gives that the force is going up, or the palm is going up. And indeed, that's what we see, right? All of these positive charges feel a force that pushes them upward. And any negative charges are going to do the exact opposite. They're going to feel a force that is pushing them in the negative direction. So we get this separation of charge where the positive charges are gathering at the top and the negative charges are gathering at the bottom. This is just because we have a conducting rod that's moving through a uniform magnetic field. And the force that causes these to move up or down is given by our magnetic force, right? F is equal to Q times V times B. This is an equation we saw back in chapter 21. We've just plugged in that the angle between the speed and the magnetic field here is 90 degrees. So sine of 90 is indeed 1. So that's why this equation is a little simpler here. So we know the force that is moving those charges. Now we could take that same conducting rod, and instead of just being a random conducting rod in space, we're going to put it on this conducting rail. So it's a piece of metal that's conducting, and it's wired to a light bulb and around to the other side of the conducting rail. If we then move that conducting rod again, we're going to get a separation of charges, right? The positive charges are going to go up, the negative charges are going to go down, but now we have a complete loop that those positive charges don't need to stop at the top. They can keep right on going. And this forms our current, right? Standard current is in the direction that positive charges would move, and the opposite direction that negative charges would move. So we've now induced a current as well as induced an EMF. This is known as motional EMF because it's tied to the motion of the conducting rail. It only happens while that's moving. But because of it, it's a very clear effect. The light bulb will turn on just by moving this bar. Not having a battery, we've managed to create a motional EMF. And the key there is it's amotional, not emotional EMF. Emotions can be addressed another time. Here we're just focused on things moving. All right, now we can show that the motional EMF, when the velocity, the magnetic field, and the length are all mutually perpendicular, right? That is, the rod length is perpendicular to the magnetic field and the speed, that the EMF that's induced is given by the speed that the rail or rod is moving at, that the rod is moving at, times the strength of the magnetic field, times the length of that rod. So that gives us a way to calculate how much EMF is induced. And remember, our symbol for EMF is the scripted E. It's cursive like so. Every once in a while, it comes out more scribbly. But either way, you can look for that scripted E and note that that is our EMF variable. All right. So now that we have this equation, which you can derive, I believe there's details in the textbook if you're more interested in knowing where it comes from, But let's see what we can do with it. Example 1. Operate a light bulb with motional EMF. Suppose the rod is moving with a speed of 5 meters per second, perpendicular to a 0.8 Tesla magnetic field. The rod has a length of 1.6 meters and a negligible electrical resistance. The rails also have a negligible electrical resistance. The light bulb has a resistance of 96 ohms. Find A, the EMF produced by the rod, and B, the current induced in the circuit. All right, so let's take a look at what this problem has given us. Right, first it mentions the speed, so that's going to correspond to our V. And then they mention 0.80 Tesla magnetic field, that will correspond to our variable capital B. And then it tells us even the length of the rod. So that sounds like our L. We're now in very good shape to calculate our EMF, since we know that our EMF is equal to V times B times L, since they are all perpendicular here. What about if we want to find the current induced in the circuit, how much current is passing through? That's where we're going to need to pull in an idea from back in chapter 20, right, of how is current related to our EMF. And you can think of it as V equals IR, or EMF is equal to I times R. So the current will just be the EMF divided by the resistance, and it tells us that the rod and the rails both have negligible electrical resistance, so our only resistance is this 96 ohms. So with that, we're in pretty good shape to solve. Let's take a look at the math. All right, our EMF is equal to VBL, so that comes out to 6.4, and the units here, Teslas have some other things packed into them, so if you multiply Teslas by meters per second by meters, it comes out to units of volts. As long as you use this given equation, it's okay to trust that the units for EMF are what we'd expect, that is volts. But if you want, you can look into the units of how Teslas break down to see that the volts do come out. And then for the current, that's going to be EMF divided by resistance, right? So 6.4 volts divided by 96 ohms, so it comes to 0.067 amps, which is a pretty reasonable current. That's enough that it can turn on a light bulb. Since we have a light bulb on, we could think about the power, right? We know that power is equal to current times voltage, so we could take our current and our EMF, and that would give us the power. We could also think, okay, what if we had another light bulb connected? What would that do? Well, if you remember, it'll depend a bit on how we wire that light bulb, if it's wired in series or in parallel. But if we wire that light bulb in series, that's going to increase the resistance and decrease the total current, as well as the power output for each of those bulbs. Now, as we're thinking about power, a closely related topic is electrical energy. So if we think about this rod moving and it's turning on a light bulb, where is that energy coming from? Is it just magically free energy? That would be nice, but we know that there must be a source. And the key is that the hand, let's say if it's your hand moving it, that's moving the rod, is counterbalanced by another force that's created by the magnetic field and the moving charges, right? So we already used our right-hand rule to see how the current is created in terms of the force moving the positive charges upward. But now we could use the right-hand rule a second time, the same right-hand rule, and set our velocity as going up, because now these positive charges are moving up. The magnetic field is going in. And so with those two things, that gives us the magnetic force is backward on the rod, or to the left of it. The hand then has to exert a force to the right to keep the bar moving forward. And those two forces will be exactly equal and opposite. So the current times the length times the magnetic field. And that tells you how much magnetic force there is once this current has been induced. Now we know that the force has to be going in the opposite direction as the velocity, because if it was going in the same direction as the velocity, like if the current was flowing in this clockwise direction to create a forward force, then we'd be getting free energy, right? We'd be going that way, creating a current and actually helping our speed go faster and faster. Where's the energy coming from, right? The energy always has to come from somewhere. We can highlight this idea with a conceptual example, conservation of energy. The conducting rod is free to slide down between two vertical copper tracks. There's no kinetic friction between the rod and the tracks. Because the only force on the rod is its weight, it falls with an acceleration equal to the acceleration of gravity. Suppose the resistance is then connected between the tops of the tracks. Does the rod now fall with an acceleration equal, less than, or greater than the acceleration of gravity? So I want you to think this through before you go on. So come up with an answer, and in the meantime, please pause the video. All right. Hoping you pause the video. Let's take a look. So if we wire this, where we add a resistor between the vertical tracks, notice now we have a complete loop, right, where the current can flow through that resistor. So if we're then inducing a current and an EMF, once we have a current flowing, that's going to create a force that acts on the rod. And the quick answer here is that force is going to oppose the direction of motion. So that force is then going to be upward in this case, force due to the magnetic field. But we can also double check that with the right-hand rule. So if the bar is going down through a magnetic field that's coming sideways through it, initially the charges are moving down, the magnetic field is coming out to the right, and so the current, it looks like, will be going like so. Let's see, yeah, because moving down, magnetic field off to the side, and so then the positive charges get pushed like so. Now if we line our thumb up with the current, but also keep that magnetic field pointed outward, that gives me, and this is really hard for you to see, that gives me a force that's going up. A finger that's pointed up there. There we go, this is a little easier, right? And so that's why the magnetic force is indeed upward. Now, if the magnetic force is upward, that's opposing the weight of the object, so that means our overall speed or acceleration will be less than that of gravity. And here we have the full diagram as drawn. All right, so this introduces motional EMF. There's a lot more to come and to see how this connects to the bigger idea of electromagnetic induction. Stick around.